So thank you for the generous introduction, and thanks for the invitation to deliver a talk in this meeting. It's an honor and a privilege for me. So I shall begin my presentation by sharing my screen. Is my presentation visible?
Yes, yes.
Yeah. So good morning, everyone. So today I'm going to speak about some introductory aspects of geometry phase. So I'll not go into a lot of technical details. It will be just you can say, a dive into this beautiful world, and hope that you will enjoy the ride along with me. So let us begin by some bit of history. Euclid, the famous Greek mathematician, is known as the father of geometry. We all have learned geometry, whatever school level geometry that we typically are taught, more or less comes from this book. The book is called Elements. It's a famous book, and so famous that for several centuries, or maybe a millennia or something, it had dominated the mathematical thinking of Europeans and to a certain extent even Indians also, especially the geometrical aspects. Whereas when we are taught geometry in the school, we are taught these axioms. Not many a times uh, we may not be told about that these are actually Euclid's axioms, but we are taught certain axioms, certain postulates. So one of the famous postulates is that there exists a straight line between any 2 points. So you give me any 2 points, and then I can always draw a straight line. That's the postulate of Euclid. And if you have any segment of a line, any short piece of line, you can extend it forward and you can extend it backward indefinitely. You can keep walking along the lines in a straight manner, back and forth, both the ways. Similarly, you can draw a circle if you give me a center, and if you give me a radius, then using a a rounder compass instrument, I can always draw a circle. That's always possible. Fourth postulate is that all the right angles are equal to one another. So there is nothing special about one right angle to another angle. They are equal. And the fifth postulate is that two parallel lines never cross or meet one another if you extend them to infinity in either directions. So a simple example is that if you walk on a railway line, and look at the horizon both ways, on the front side and the back side, you may tend to think that the lines, the railway tracks are going to intersect, but they never actually do. Because you can travel, you can walk indefinitely and see they never intersect. But it gives you a feeling that they do. That's the problem of our vision, and other you can say shortcoming of our finite magnification. So the idea is that if you have two lines A and B, which are drawn here, and which are at right angles to any other line, then they never cross or meet one another if you extend them to infinity. This is very famous. It is called the parallel postulate. So a lot of people in mathematical community for many years thought this was okay. This was there is no reason not to believe the veracity of this postulate. Until in the 19th century, study of geometry, the modern geometry that we know of, was initiated by Gauss. And the reason was very peculiar. He had inherited apparently a lot of land, from his father, his family, and but a lot of this land was on curved surfaces. It was on slopes, and finding the area was very tricky. We know how to find an area of a flat piece of land, but if it is curved, it is on a slope, for example, If it is on a regular slope like a sphere or a cone, then it is easy, the formula is known. But if it is on a general non-regular slope, then it is a tricky issue. How do you go about finding the the area of the line? So Gauss started asking these questions. Hello. So he started asking this question that how do you define even a notion of a straight line on a curved surface? What do you mean by straight line? The surface itself is curved. Well, the simple answer one can give in this example that you suppose you have a spherical surface which I have drawn, and you have suppose 2 points A and B on the surface. And on this surface you walk along and find the shortest path, the path that takes minimum distance while you are on the surface. So you see that this blue curve which connects these 2 points A and B is the shortest. All the other curves, they take a longer time or longer distance. So that is a good definition of a straight line, and this is taken from the usual that on a non-curved planar surface, the line connecting the 2 points has the shortest distance. So that is the criteria which you have picked up to define a straight line. In literature, these curves are called geodesics. And they are very useful in general relativity and other places. In particular, in a sphere, if you extend this line, blue line that connects A and B, you can extend it indefinitely. Not indefinitely, you will be figure. If you extend it on both the sides, you find that it forms a great circle. It forms a circle like an equator, which is passing the whole sphere. So, for example, this dark circle that you see is not a great circle, but this one is a great circle, the blue one. So those great circles are, you can say lines, the shortest distance lines connecting 2 points. So that we are able to figure it out. But a peculiar situation happens. If you take two black curves, 2 great circles, for example, which are drawn here, which intersect the equator exactly at 90 degrees. You can think of them as 2 longitude lines. If blue curve is the equator, if this sphere is Earth, and these 2 black curves are longitude lines where the longitude is constant, and you walk along them, they meet at North and South Pole. So, but they are supposed to be parallel lines because they intersect equator exactly at 90 degrees. So, very peculiar situation you find that parallel lines are intersecting, not only once but twice. This situation does not happen if you open the, if you don't have this spherical surface. If you have a blackboard kind of a surface or a flat surface, situation doesn't happen. It happens because the sphere is closed and it's curved. Another peculiar situation happens that the intersection angle on the North Pole between the 2 lines is theta. And if you add up these angles, so 90, 90 and theta, if you look at the triangle, which is formed by North Pole P and Q, the sum of the angles of the triangle is greater than 180, which is very peculiar, which is very bizarre. Because we are brought up with a geometry where, angles exactly add up to 180. So this was a bit of a surprise to Gauss and his successor Riemann and other mathematicians in that era. That is what is going on. And several strange things like these happen. So some people dismissed that, Euclid is a father figure, so we should respect his postulate that parallel lines should never intersect. So probably a lot of mathematicians gave up on the definition of great circles as parallel lines. Uh, some people give up geometry completely. Like we are only interested in planar geometry, non-planar geometry. It's not. We are not going to get into it. So, but geniuses like Riemann and you know Gauss, for example, initiated the study and understood that well these you have to understand the curvature of the surface in order to gain better insight into these kinds of things. So that why how do you define curvature of a surface? If curvature is not there, things are okay. If curvature is there exists a curvature at some point, your lines will behave in a weird manner. Your geometry, so to speak, will be very different from the usual planar geometry. Rules and results of planar geometry no longer hold. So the quest began to define what would be curvature. How do you make sense of it? You know, one definition, but beautiful definition that eventually came along was that of parallel transport of a vector along a closed loop. So suppose I have a vector. Let's say this is given in the green color. And I maintain that I will keep, you can think of this as a long rope, a long rod or a long bamboo, stick. So you agree that at North Pole, you'll start walking towards point P from North Pole along the great circle, along the constant longitude line. You'll start walking. And when you are going to walk, you are pointing this vector on the backside, towards your backside at the horizon. So you will point it along the line, you will carry it along the line, you will not turn it, twist it, whatever, and at each point you will align it along the horizon. At each point you will check whether my bamboo is exactly aligning with the horizon or not. If it is not, then you shift it, make it horizontal, exactly horizontal. So you take it along nicely, and you will come to the equator, point P. Now here you go along this curve on the equator, walk till point Q. But now you say that well, I keep it again aligned to the horizon where I'm walking. I will not turn it, I will not twist it, and you come till point Q. Again you do the same job. From Q you start walking to North Pole, keeping it aligned to the horizon. And surprisingly, what you find when you come back, you find that the position of the bamboo or the vector changes from the original position that you had started with. It's a very peculiar sort of a thing that you are parallelly dragging a vector parallel to itself. At each point, you are ensuring that vector is parallel from its previous location. If vector was at this point, as you move along, you keep it aligning it to the previous orientation carefully. And you find that when you return, there is a change in the original position and the final position. There is an angular change. There is a small angle that you see, it changes. And it was found out that if you do this experiment or do this procedure on a flat surface, no change occurs. You won't see this change. This change occurs because of the curvature of this, surface. That is the main, sort of main ingredient giving rise to this phenomenon. And it became very popular to understand curvature in terms of this angular change. And the curvature defined in such a manner in modern language is called the Ricci curvature. And this angular change gamma, sometimes it is called holonomy, or sometimes in physics literature it is called anomalomy. But it is more popularly called as the lack of parallel transport of a vector along a closed loop. That in third space, a vector cannot be dragged parallel to itself, without changing the orientation. and that is a measure of curvature. So a lot of beautiful ideas of general theory of relativity. Yeah, sure. Is there any question? Yeah, so a lot of beautiful ideas of general theory of relativity can be introduced or are introduced in terms of this parallel transform of a vector along a closed loop. So you may say that, well, but we are interested in quantum mechanics, quantum computation, and why should we really bother, about these things? After all, we live in the world of vectors, and that is good enough for matrices. But then you see that here also you are talking about vectors, dragging vector on a surface. But then your question can be that, well, but do we encounter such surfaces in quantum physics? And I would say yes, very much you do encounter. Let us see how does it come about. Well, let us take the simple problem of a qubit. I'm sure all of you are familiar with qubit. Qubit can be thought of as a simple vector in a two-dimensional complex Hilbert space. That means that there are two orthogonal basis vectors here, which are given as 0 and 1, and they are orthogonal to one another. They are unit vectors, and they are being multiplied by two coefficients alpha and beta, which are complex numbers. So you can also write this in a form of a column or a row matrix if you want, but this notation is like slightly simple for our purpose. Qubit can be thought of as a simple realization of a electron with upspin and a downspin. So if you localize an electron somewhere, on an atom or quantum dot or whatever, and you have frozen it somewhere so that it cannot move around, and you can apply magnetic field and align it in up direction, or apply the reverse magnetic field and apply it in down direction, and up and down directions for electron. The spin directions are orthogonal because they are eigenstates of spin operator. So you can either represent them as spin down state, spin up state, or more simply 0 by state 0 and state 1, which I have done. Now, the idea is that complex number alpha can be written in terms of a phase e to the power I5 times mod of alpha. So the same you can do with beta. Mod, you can put a mod and put a separate phase. Which is, what I'm doing is I'm just doing the polar decomposition of this complex numbers. I can pull out this e to the power I5 outside the bracket, and I can just write here chi minus 5 as the phase. Now, generally, to make life easy, it is advisable to work with normalized vectors, not general vectors like psi. Normalized, with normalization, I mean that its norm is 1. Because 0 and 1 are orthogonal, it actually means that mod alpha square plus mod beta square is equal to 1. It makes life very easy. A lot of manipulation becomes very easy. It's not necessary, but usually that is the case. But life becomes very easy. So it's very reasonable to put a condition on alpha and beta. And now comes a very interesting aspect of quantum mechanics. We are all told about vectors, that quantum mechanics, we are only bothered about vectors and stuff like that. But actually, quantum mechanics, the physical reality, is slightly more than vectors. See, the point is that if you have two wave functions or two states, psi and e to the power I lambda times psi, then they are not physically distinguishable. There is no single experiment which can distinguish them. So these are, mind you, these are separate vectors. They are collinear. They are collinear vectors, but they are separate vectors in the sense of vector space. But they are physically distinct. You can never distinguish them. In other
এই যে
words,
এগ্রিক নিয়ে প্রস্তুতি দিয়ে চলছে। হুম। আর
in
ওখানে
other
আমার লেকচারের জন্য বসে আছি।
in
তুমি
other words,
শুনতে চাও, শুনতে পারো, ভালোই লাগবে।
sorry, can somebody switch on their mic? It's interfering with what I'm
Prof,
speaking.
When the speaker is
So, in other language, in quantum mechanics, what you measure is not the wave function psi, but rather the probability. And probability is immune under such, factors. You change the psi by an angular factor, e to the power I lambda, and probability doesn't change. Well, you can then argue that, well, but what about averages? Well, averages also are in this combination that you have a psi star that you multiplied with psi, sandwiched with an operator. So an angular factor from psi star and an angular factor from psi, they always cancel each other. So although we are calling Hilbert space to be the physical, like mathematical space, but there is a lot of overcounting apparently that's happening by working with Hilbert space. So it's a good idea. It's a wise sort of a proposition to work with a collection of these vectors. So you will collect psi and all its collinear vectors, unit normalized collinear vectors, into one box, and we call it a ray. So you have a vector, and then you extend it, by multiplying the phase, and you will get infinite family of vectors, each differing by a phase, and you club them all together, and what you get is a ray. Actually, what you get is a pure state density matrix, because this ray is same as pure state density matrix, but nevertheless, let us work with this ray representation. So the idea is that the space that we pulled out e to the power I5 is really not physical. We should not bother with it. It can be ignored. But whatever is left is physical. So whatever is left is we have mod alpha, mod beta, and then a phase hanging around here. And this condition tells us that mod alpha and mod beta can be written in terms of an angle theta. See, idea is that alpha square plus beta square is equal to 1. And this resonates, this is very similar to cos square theta plus sin square theta is equal to 1. So I can say that mod alpha is like cos theta and mod beta is like sin theta. And then there is a phase. So that's the idea. So in literature, people use theta by 2 for simplicity, for other reasons, but you can use theta as well. And the phase, I'm calling it the rho here, e to the power I rho. So this is whatever you have gotten it here. This is physically distinguishable in terms of experiments, in terms of its manifestation. This factor that we have pulled out is unphysical. So we don't bother. Now, when you have two angles, describing your vector, so psi is completely described by just two angles, theta and rho. When two angles also describe a sphere, you have, when you go to the polar representation on a unit sphere, for example, radius, we take it to be 1 for simplicity. And then, you can have a polar representation of each point on this sphere in terms of an angle theta and rho. So we find that all the qubits which are physically distinguishable, which are different, they are all groups. They are all actually living on the surface of a sphere. So you see that we started from vectors, simple two-dimensional matrices, if you might want to use that language, which was just an algebraic construction. Vectors which you can add them nicely, you can multiply them nicely, you can take their inner product, you can find their norm, for example, all the properties that constitute a Hilbert space. And then, we have ended up on a geometrical structure, which is surface of a sphere in this case. This construction is well known. It is very old, and sometimes in the literature it is called Poincare sphere, especially in optics, and block sphere mostly in quantum physical context. So you may ask this question that, well, is it unique to this qubit system? Is it special? Answer is no. Poincare sphere in particular also, historically it was used in the context of polarization optics. The polarization of light also behaves like qubit, as you might be aware. So there are two orthogonal polarization states, vertical and horizontal of light, and you can also, in a suitable manner, you can treat them as qubits. So the idea is that space of rays are not vectors. So one must remember that although I'm using a vector to write, I mean, I'm using that point P corresponds to a vector psi, it actually doesn't correspond to a single vector, it corresponds to infinitely many vectors. So it doesn't form a vector space really. It forms a different space. It's technical to get into it right now. You can think of it as a surface. It forms a surface, a smooth surface, a sphere in this case. So this is the space of rays that is actually physical behind the Hilbert space, where you should be working. But now you are immediately into the game. Euclid is gone. Gauss and Riemann and others are into the game. You have curvature coming in. You have, along with curvature, all the ideas of geometry will necessarily find their way in. So you can ask this question that, well, what about parallel transport? How about curvature? How about many other things, metric, for example, for advanced students and stuff like that. And in 1984, Berry asked the same question for parallel transport. He said that we take a vector psi, it depends upon a parameter L, and I drag it along a closed curve, like we did it here in this figure. The way you drag the vector along a closed loop, and you came back and you found a change in the angular shift. So he asked the same question. Suppose I do the same, on a general vector. He didn't even bothered about qubits. He said it on a general vector space. If I do it, what do I get? What is the angular shift that I get? And he gave this formula that if you do it, you take your vector psi, differentiate it with respect to the parameter that you are defining, that is used to define these states. Take the inner product, integrate over the loop, closed loop, and whatever you get is called the geometric phase. Here we are assuming psi. Here we are assuming these vectors to be unit normalized. So in case of qubit, you are on the surface of the sphere. These are unit normalized vectors. And when 1984 he introduced this, notion, it generated a lot of interest. So a lot of people from the various branches of physics immediately were captivated by these ideas. So immediately Thouless, or sometime around the same time, Thouless wrote a famous paper in Hall effect, having similar ideas, and Professor B. Simon, a mathematical physicist, wrote a beautiful paper unifying these ideas, that ideas in which were predominant, which were used by Thouless in Hall effect context, actually are very close to these ideas of geometric phase. Around the same time, there was a beautiful paper by Provost and Valley where they gave a notion of metric. That people who are familiar with general theory relativity find interesting that on this curved surface, you need to describe it in a certain geometric sense. You need to read the notion of metric. It tells you how the curvature is changing, stuff like that. And that was given in that beautiful paper. So along 84, 85, around that era, 83, 84, 85, a lot of beautiful ideas came along. This work. Later on, it was found by Berry after a couple of years. So Berry's phase basically tells us that how much phase is acquired by a state when it completes a circuit in the equal space. So you can ask this question that suppose I go to the block sphere, I take 3 points, P1, P2 and P3, and I form a triangle out of them. Now, remember that when you are forming the triangle, you connect it via the segments of the great circle. So these lines which are joining P1 and P2 are straight lines as per the rule of circle, as per the rule of sphere. Okay, so you join them along, and then you can ask this question that suppose I travel from P1 to P2, P2 to P3, P3 to P1 back. How much phase would my state acquire? Well, to surprise of Berry, this question was answered long back by Pancharatnam in 1953. Pancharatnam was a researcher at Riemann Research Institute, what is now called Riemann Research Institute, and he was studying polarization in optics, how polarization state changes when it is subjected to various polarizing crystals, and he discovered this effect. And he gave the beautiful formula that you look at the solid angle, calculate the solid angle subtended by this triangle from the origin, and you half it. That will give you the angular change. It's a very, very famous formula, very useful formula also. Like half the solid angle formed by the 3 points of the triangle on the scale. And the algebraic expression is that if psi 1, psi 2, if psi 1, psi 2, and psi 3 are the 3 vectors which are forming the triangle, then you take inner product, you look at the cyclic inner product of psi 1 with psi 2, psi 2 with psi 3, psi 3 with psi 1 back. So it is cyclic. And multiply them and look at the angle, the argument of it, and that gives you the angular shift. People who are familiar with density matrices may find it more appealing to look at the formula as a product of 3 density matrices, rho 1, rho 2, rho 3. Take trace of them and look at the argument. So this object behaves like an area. So that was the big discovery. Notion of area, which is an inherently geometric notion, how does it come into the algebraic structure of vectors? So this was a big discovery. Of course, Pancharatnam didn't live long to see fructification of this discovery, but it only in 80s it was well understood eventually that the importance of this discovery. So you may ask that why am I speaking in this conference about it? What is the use of it, for example? Is there any technological or physical use of it? That can be a question. Eventually it was found out that it plays a very important role in many interference phenomena. So, several interference phenomena, because especially involving polarization, it plays a very important role. So these days there are a lot of works that are going on looking at angular momentum of optical beams. Angular momentum of optical beams, how it is, interacting with the spin angular momentum. So angular momentum, as in there will be 2 components. One will be the orbital angular momentum, and another will be the spin angular momentum, or the polarization of the photon, and how they are interacting. In such interference experiment, geometrical ideas are very naturally found to play a role. Other use eventually from Hall effect and later on in the development of topological insulators, it was eventually found that these geometrical ideas are inherently connected to the topology. Topology is the global nature of the surface, whether it is closed like a sphere, or open like a plane, or whether it has holes like a torus, for example, which has a hole in between. So those kinds of things can also be captured by these objects. Geometric fields and related ideas can capture topology also many times. For example, Aharonov Bohm phase can be understood as a special case of geometric field which captures topology. And the point is that if you use these ideas, you can construct quantum states which are immune to disorder, which are immune to disturbances, which whose coherence is protected. Such phases can also be manipulated by measurements. You can subject your state to various measurements and you can manipulate the phases. So this was done by Professor Samwell and Bhandari in their monumental work in 1987. They were able to see occurrence of these phases via measurements, and immediately it was followed up by Anusandhan and Pines. Essentially these measurements are incomplete. You are not completely projecting the state. You are only projecting a part of it. Then they give rise to what are called non-abelian phases. I have not gotten into it, but they are very interesting. Non-abelian geometric phases and stuff like that. You might wonder that why do we need so many non-abelian geometry? Why do we bother? Well, it was eventually found that they give rise to these peculiar objects called anyons in condensed matter systems. In steel systems, you can have these peculiar objects called anyons, which are neither bosons, they are neither Fermions, they are in between. So they are like, it's a very different world that when they live in fractional spins. You can have objects like fractional charges, and all these can be, in particular, when you have something called anomaly, chiral anomaly coming into picture. Which it does in many condensed matter systems. It can give rise to charge fractionalization. So you can have these anyons which are like half electrons and stuff like that. And these objects have now been realized in laboratory in a clean manner, and there is a whole branch of computation called topological quantum computing, which is based essentially on these ideas. And this whole subject owes the genesis to the notion of geometric phase. So geometric phase has enormous technological applications, and only now people have been able to realize them, many of these things in a clean manner in experiments. So we are hopeful that a lot of interesting computation business can come using these kinds of objects. This is my last slide. I've just done some small work recently where I'm able to sort of show that geometric phases are not this geometric phase that we have written down here, for example, this formula is not the only one. If suppose for some reason your experiment or your setup doesn't have the geometric structure available to you, then one should not be disheartened. It should not feel sad. There can possibly be another structure, geometric structure on the same footing as the previous geometric phase, with a slight difference that now you have an operator O coming in this formula. You have this average coming, divided by this object. So O is a Hermitian, an observable, well-defined Hermitian operator. So you can still define a geometric phase like that. And now its manifestation can come in the averages. Average, when you look at average of this physical observable, it will have a signature in these. It can also affect your energy levels. Certainly. So my take-home lesson or take-home idea that I wanted to share with you is that there is a lot of geometry waiting for exploration in quantum systems, and potentially it can give rise to new interesting physics and new interesting technologies. So hope that some of you explore and benefit from it. So I think I'll stop here. Thank you. And take some questions if there are any.
Thank you, Vyas. Thank you for setting the scene for fundamental aspects of this. So I request the participants to ask questions. Any questions? Am I audible?
Yeah, you're audible.
Thank you. So I see application of quantum sensing. You know, this phrase very useful for quantum sensing. Can you comment on that?
Yeah. Quantum sensing, so a lot of quantum sensing involves interferometry, very careful interferometry. And you would want to enhance your, the interference signal from the noise. And there some of these things can do the job that if your phase is protected by topology of the surface, underlying surface, then under small deformations, it's not going to change. In fact, under a lot of perturbation, it has been theoretically shown in many cases that it won't change significantly. And if you use such states, or if your setup involves such space, then you can have a robust signal in sensing, which is immune to a lot of noise. So that is something that people can look up. I mean, that is something where it can potentially find a lot of applications. So, for example, in topological insulators in condensed matter, it is found that you introduce a lot of disorder in the system and other external perturbations. Under such things, the geometric phase survives; it doesn't change, and it gives rise to robust electronic flow, propagation, conductivity doesn't change. So that is one technological sort of use. So it's confirmed that topology protects you from disorder and noise. That is a confirmed.